following on from the presentation from OneSpin about this technology, we've now got Darren Galpin from Infineon, who's going to talk about the usage of OneSpin Quantify. Darren is the system and IP manager for Infineon in Bristol, having worked at Infineon for 14 years, previously working at ST Microelectronics in verification and product engineering roles.
Right, so I'm going to go through in 10 simpler slides what Wright went through in 30 and describe the usage of the Quantify tool. Okay, so what exactly is it? Wright showed us some pictures of it. It's basically a tool for gauging the quality of your properties and assertions using all of the available properties and assertions you've got. So if you have assertions embedded in the design as well as a handcrafted property environment, it will quite happily run them all, whether they're in PSL, SVA, the in-house ITL language, VHDL assertions. So if they're there, it will use them. And basically, it generates a structural coverage metric for the code under test. You'll find there are plenty of designers who still have a mental block that properties are very, very hard to understand and don't want to look at any results. And completeness checks and things can be very difficult to get them to look at, but if you present them with something which looks a little bit like structural coverage, then they're much happier. And you can use it to identify holes in your formal environment which completeness checks may have missed, because you have to sometimes change the structure of your property to fit in with the completeness idea. You have to tell it how to bring things can sometimes get through. Or if you've got constraints taking particular scenarios out, this will help identify it by showing holes as a result. So how do you run it? Ideally, you run all of your properties in the assertion studio tool once so that you can prove which ones pass, which ones don't. And to speed it up slightly, you can generate a witness, which is an example of it passing, and then Quantify uses all of that information together to start its run. And it's as simple as typing Quantify on the command line once you've got it right. It doesn't actually require anything else for you to add in, although if you want to use it in an iterative mode, you can run it over a small set of properties, save your result, write a new property, and then iteratively run that one on as well. And then you wait. For some environments, it might be a few minutes. For other environments, it might be a few days, and then you analyze the result. When you run, this is pretty much what you see. So you've got on the left-hand side of the screen a list of all of the properties, assertions you've got in your design. OneSpin tells you with color coding whether they pass, whether you've got a witness or not. And then it gives you a summary table showing you what the state of play is up to now. So this table gets regenerated as it progresses through the stages more and more. It basically tells you any of the code you excluded from being analyzed, any code the tool thinks is redundant, so it's not going to analyze, any verification code, so assertions that have been put directly in PRTL, for example. And then it gives you a set of results showing you what it's working out about the designing your environment that you're running through. So we'll now go through this section in a little bit more detail on what these mean. Basically, it has the idea, as Wright said, of observability and execution. So it's kind of splitting its analysis into two parts. So the one bit is, can I actually execute the line in the first place? And the second bit is, having executed it, or even if I can't execute it, could we see an effect of that line on within a property or insertion somewhere? So covered was the first line in that table, and that means the line of code was actually physically executed somewhere in a property, so it featured within the kernel object going in, and the effect of that line was observed. So therefore, if there was a fault somewhere on that line of code, you should have seen the effect. Basically, one of your properties would have caught it and generated a fail. So in that sense, it's very similar to certitude, but it is different. The way it handles it is slightly different. Then you've got reached, which was the line of code that was executed, but the tool couldn't formally prove one way or the other whether a fault on there would have been observed or not. So it's the equivalent still to data coverage from a traditional simulation. No lines being executed, but you don't know whether you would have actually picked up a flight there at all or not. Then you have unknown, which is we didn't execute it, we don't know if it can be observed, so no idea what to do. You need to go away and do something in the property somewhere to try and pick that one up somehow. Unobserved, we executed the line, but it doesn't actually know whether it was would be observable or not. It. And uncovered, well, we know that the line's not executable, but we didn't even have a property which tried to execute it in the first place. And furthermore, you've got constrained, which is we've got lines of code which were not hit, but they were hit due to constraints in the property physically excluding the tool from exploring that space, rather than it couldn't actually get there because your properties weren't good enough. Once it's been completed, you can generate one of two reports. First is an HTML report, and that is a hierarchical report where it goes down into each of your files and displays the results in a color-coded form. Luckily, it also uses symbols here to identify it, so those of you who, like I do, have an engineer who's colorblind doesn't get completely lost. Basically, it gives you green for good, red for bad, and various shadings in between to try and give you a good, easy representation of the results. What it generally does is it lays out for each of your files a line like this just to summarize each of the different types, and then you can drill down for each file and then go through on a line-by-line basis if you want to see what's there and what you might want to do about it. The second report you can generate is a UCIS compliant XML file. And this is particularly useful because we can then write out the coverage data from OneSpin, and now we've got it in an industry standard format. We can then link it with coverage data from other tooling. So on this particular block I'm working on now, we are running properties to probably test 80 to 90% of the block, but due to the state depth of the design, it's very difficult to fully formally verify it over all cases. So we're also running it with random test messages, but the problem then comes is how do you avoid verifying the same thing twice? What you can do here is run your random simulations, get your structural and functional coverage results out of that, get your simulation coverage data from OneSpin as well as the property pass-fails all in multiple UCIS compliant files, load them into a tool such as a SureSign, so you can then have all your coverage in one place. So if I've then got a verification plan for my entire design, I can then map it to the coverage, and it's agnostic at that point which tool it came from. I can either say, here's a property which passes it, here's some structural coverage over here from the formal tool, it passes it, I've got formal structural coverage from the simulation tool for proving the other parts, and in that way you can bring it all into a coherent whole. Thus, you can, if you've got holes in your structural coverage from your simulation, you can use your formal results here for closing those holes without necessarily needing to work hard on your random test bench. So the pros and cons of using this: it leverages all of the assertions and properties within the environment. So whether your design has written them, embedded them within the design, saying these are the things I expect to happen, whether the verification engineer has written formal properties to try and prove functions, they can all be used together. The results are easily understood, so anyone who's used to looking at structural coverage can look at the report from OneSpin and analyze it. It doesn't require specialist knowledge. People tend to fear it slightly less because it's slightly more what they're used to. And it easily shows holes in property coverage. So if you've got a piece of code which is uncovered, or basically not in the reach section or cover section from OneSpin, you know you've got code you really need to go off and write some assertions for, or something to go and check. And when merging the coverage data in the SureSign, as we do, then you can use two approaches for proving the whole rather than having to try and prove it all in one thing and then perhaps all again in another. The cons, and this is one we particularly get hit by, is long property time snowball the quantify runtime. So in this particular example I have 40 properties, one of which takes about 8 hours to run, all the others take 10 minutes or less. And as a result, it takes 4 days to run Quantify over that completely. So it's not quick in this particular case for a turnaround. However, we have smaller environments where I can run all of the properties in 2-3 minutes, and you can then turn that around in half an hour. Because again, you're rerunning effectively a property multiple times to prove the effectively the observability. You've got one property which is particularly testing one area, which none of the others are going to get hit, as you have to run it more times. And as with structural coverage, it only shows you that you've tested what is there. It's not going to prove that you've tested any function if it was physically missing from the design. For that, you're going to have to do more of a functional analysis of your properties to make sure that you've tested everything. Subject's going to be a quick talk, but that is basically it. A quick round through.
Okay.
Thank you. That's okay.
On your last folder, you mentioned long property times, and I was wondering, in both talks, there's been nothing said about design for verification. In fact, can we push something forward to the designers so that they know that actually if you do it like this, it's going to take a longer time to do?
In this particular case, it's rather difficult to say that, because the particular property I had is I freed up a busy signal to come in at any time. And for whatever reason, it snuggled up the time on this property from 20 minutes to 8 hours. And I'm not sure that a designer really could have done anything about that. However, any design where you're cross-multiplying things together at the same time is going to create a bigger space to go into. So if you can code things more simply, it's going to be simpler to prove. I regularly whinge at my designers. I don't necessarily think it has any result in the code complexity.
Very cathartic, just to whinge at designers, isn't it? Okay, Ruby.
My question's also about the long property times. I was using an IFV flow from Cadence with Certitude to do something fairly similar, and I found that I didn't need to run my properties until they passed, because it's injecting mutations. They were fairly gross errors, and I basically took a lack of failure within actually 10 seconds of running my properties to be mainly, that is not detected a fault. And although some mutations did take, I was able to rerun just the few that weren't detected in that time. I was able to run those with longer times. That dramatically reduced my the amount of time it took to run the properties. So I'm surprised, or I just don't understand why they need to run for so long, I guess.
As I said, most of my properties are short, but in this particular case, allowing this extra parameter input to vary freely at any time has somehow massively increased the kernel logic flowing in to the property. Yeah? Because it's not just I have more lines of code now, I have more lines of code over however many cycles it takes to propagate into the property. So I can't easily say why this one property took so much longer than the others, because I have another property where I've allowed the same signal to vary, but within a slightly more constrained time window, and that passes in 30 minutes, I think. It's just this one particular case. There's one particular combination of events which is snowballing and massively expanding the kernel logic feeding in. And at the moment, I have no way of easily knowing why or how to go about breaking that down to make it simpler. I'm not aware of anything in the tool giving me the kernel logic where I can then go and prune something and break it down.
Okay. There's another question from Bristol, Rigish.
So my question is more on your experiences of UCIS and how you have managed to actually merge in the coverage data and be able to track back with a vPlan.
Very good question.
And how long have you got? Right, so currently we use the API from Cadence for extracting the functional coverage and structural coverage results out of that and putting it into the AsureSign, which is what we're using for our verification planning at the moment. So our flow relies on taking the requirements from a requirements database, loading them in as the start of the plan, and then fleshing that out with what we want to do to go all the way down to physical checks, because working on automotive products, I have to have proof of implementation and prove that it was there. So I've got a whole set of things in my verification plan which I want to do. So from my random test benches, I want to prove that all of my checks were physically executed, and I have coverage on them to show that they were in fact triggered during simulation. I then use the, well, basically AsureSign has built into it the coverage API details for Incisive, so that I can basically point it to the functional and structural coverage data and load that straight in. The one thing the Cadence implementation doesn't do at the moment is when you're merging the data, merge in any of the exclusion files which you've built up during IMC, because it saves that as a separate file. We're working with Cadence at the moment on a solution to that so that everything's visible through that UCIS interface. In the case of OneSpin, it's a question of writing out a UCIS XML file rather than using the API. So OneSpin itself writes out the XML using the standard, and then AsureSign simply feeds it in. And then you have one coverage database with all of the coverage data in there, with simulation paths effectively down to for your showing where your hierarchy is and where your functional coverage bins are. You've got assertion path files for the assertions themselves, and also in case here structural coverage. So it translates the code you physically executed into structural coverage, so that's available there too.
I think there's a question coming from Cambridge. But yeah, if you want more information about AsureSign, then you can always ask. Brian, we've opened you up again. I don't know if you're able to. Okay. Gunoble has a question, is it? Gunoble has a question. Gunoble?
I have, yeah. It's Tim Joyce here, ST. Bit of a loaded question. Hi, Mike. Bit of a loaded question because both vendors are here. Darren, it sounds as though you've actually run both tools. How would you compare? I thought that might generate some mirth.
Have you ever seen Harry Hill?
Had to ask the question, though.
Okay. Given that I actually developed a flow for certitude as well, where we were using OneSpin on that, I probably got reasonable amounts of experience on this, although it's a bit like apples and oranges. They're both fruit, but they're subtly different. The OneSpin tool is probably quicker for testing your properties. I mean, I haven't used the latest certitude flow in their integration with formal tools, but what we did previously was take their formally instrumented code and run it through OneSpin, switching on the individual faults. And because there are multiple faults per line from certitude on the more complex lines, it was typically taking a lot longer to prove. What you would do, though, is run your properties until such time as they got to fail, stop. And I was also having problems running OneSpin if you had asynchronous code behavior. So typically you had to run all of your properties through once with none of the faults switched on, find out which faults passed and failed as a result, and then only use the ones which pass overall before running them through. OneSpin, being a native solution for OneSpin, of course, doesn't have that problem, so it was much easier for testing the formal part. On the other hand, OneSpin doesn't have any solution for testing random verification environments. So they're doing very similar things, but each has been optimized for their own area. And I think that's probably the best solution that I can...
I have a small comment here to make regarding Darren's experiment and comparison. And the comment is simply that Darren has used an integration he made himself with some support from us, while now we also have an integration with OneSpin. So I don't think the two can compare directly.
Okay. Okay, thanks, Jean-Marc. Thank you. And thanks to Darren as well. Thank you.